Okay, so yeah, so thank you all for joining. We're about to embark on this little journey. I hope it works out. Um, the idea we were kicking around was kind of let's rewire some of the robots because the robots never quite get wired as well as they should during the competition season. The summertime, we have lots of time to think about it and go back and do things right. I thought I'd also take some time to explain some of the theory that underlies what the good practices are. And this stuff is like, there's not a lot of it, but it's pretty fundamental. So the students who are here, I would encourage you to stop me and ask questions on these basic things because they're not that hard. You shouldn't think that they're so hard that you can't understand them. You should try to understand them. So if you don't understand them, ask me questions. And then we'll show you how to apply it. And then on Wednesday we'll get together and build the robot. So today we're gonna look at some theory. We're gonna look at some practical application of that theory. I've got a list of kind of just, I would call them gut feel best practices, right? A list of things that I've come up with over the years of looking at FRC robots that I think makes a good list of, if you do all these things, your wiring will probably be pretty good. And we'll talk about how we're going to address issues on the current 3504 robot, and then Tim will take over and talk about some standards on the soldering front. On Wednesday, we'll get together at the practice field, and it'll be all hands on there. We'll do some skills practicing on the bench, so just like making good crimps, that kind of thing, where you can say, okay, here, crimp this power pole, crimp this Molex connector, whatever on the bench, and inspect the crimp and do the kinds of things we're talking about to make sure it's good. And then we'll dig in and start rewiring the robot. 3504 robot we'll definitely do. Be great if some of you bring robots, your own robots, and your own mentors to come with them, and work on your own robots as well. We're calling it day 3, but really it's day 3 through whatever. In the following weeks, we'll be sort of scheduling sessions and providing support to finish the job. Okay, so the first thing, and most of you have at least heard this phrase, even if you have never digested exactly what it means, is Ohm's law. Like, Ohm's law is one of the most fundamental pieces of electrical or electronics theory, and it's the way it works is this is the key picture right here. So this little squiggly thing is called a resistor. The voltage across that resistor is assigned value, so it's higher. The way you write it is a plus and a minus. And so, for example, if I put a 5 here for this V, that means that this point is 5 volts higher than this point, right? So it doesn't necessarily mean the absolute voltage at this point is something and the absolute voltage at this point is something else. Those don't matter. What matters is the difference in voltage across this resistor. And Ohm's law says that the voltage across a resistor will equal the current flowing through the resistor times the value of the resistance. Right? V equals I times R. And of course, you all know algebra, so you can flip these letters around all different ways and make all kinds of different equations out of this one. But V equals IR is the key one to start with. V, voltage measured in volts. A is amperes, or amps is normally what we say. That's the current, and the resistance is measured in ohms. And so if you haven't thought about this before, eventually this just becomes intuitive in electronics land, but if you haven't really thought about it before, I think an easy way to get an idea of what this means is to think about water flowing. So I drew this picture over here on the right, and you can imagine that there's a tank full of water and it's under pressure, and the pressure in the tank is P1. And there's another tank full of water and it's also under pressure, and the pressure in that tank is P2. And there's a pipe connecting these two tanks. And so what's going to happen is, if the tank in the left, if the pressure in the left tank is higher than the pressure in the right tank, then the water will flow from the high pressure tank to the low pressure tank, right? And so this is very similar to Ohm's law. So here we have, just a P by itself, which is equal to the difference between the pressure on the left and the pressure on the right. It's just a differential pressure across this pipe. The flow of water through the pipe is like the current in the circuit. And the pipe itself is the resistor. Now, the one thing is that, you know, there's sort of an inverse relationship here, right? The smaller the pipe is, the higher its resistance is going to be. If you take the limit of a pipe as its diameter goes to 0, right, the resistance will go to infinity. If you let the pipe get infinitely big, then the resistance given by the pipe gives you is 0 in that case. So you have this this relationship where the rate of flow depends on the size of the pipe and the pressure differential across the pipe. Okay, and it's easy to imagine water flowing through. Ohm's law is exactly the same thing, but for electricity. So you could think of it as, instead of water over in this tank, you have a whole bunch of electrons. And instead of water in this tank, you have a different number of electrons. And so the difference in charge between those two sides is the differential voltage across that pipe. And instead of a pipe, you have a resistor, and you get this relationship. That analogy only takes you so far, and it's kind of rough, but I think it's a good way to think about it. Right? So Ohm's law, V equals I times R. I is the current flowing through the resistor. R is the value of the resistance. V is the voltage. Any questions about that? Okay, cool. So why does this matter? Well, let's ignore Ohm's law for a second and talk about what it would be really nice if the world was like. And if we had ideal batteries, what would happen is we would take our ideal battery. So this symbol right here is the symbol for a battery. This battery is 12 volts, and it is an ideal battery, meaning it provides 12 volts no matter what. And you hook it up to the robot. Okay, so the robot is an electrical circuit. The robot's not a resistor. We're not trying to model the robot by a resistor. Robot is a very complicated electrical device, and it's going to draw whatever current it wants, right? We're asking the motors to do different things, and they're going to demand a bunch of current, and they're going to suck it out of the battery. So if the robot was ideal, the voltage that the battery provides to the robot would be the same no matter how much current the robot was drawing. So if the robot drew 10 amps, the battery voltage would still be 12 volts. If the robot draws 100 amps, the voltage that the robot sees is still 12 volts. Okay, so that's what an ideal battery would be. So it's nice for little problems to think about ideal batteries, but in the real world, we don't have ideal batteries. What we actually have is a battery that has internal resistance. And so many of you have seen this before. If you put a battery beak on a battery, you know, it tells you all the stuff. And we normally look at like just the charge and say, oh, it's good. But there's this little line right here at the bottom, R int equals 0.016 ohms. Okay, so that value right there is the internal resistance of this battery. Now, a lot of you know that you can look at that value, and the higher that value is, the older the battery is, and the closer it is to being ended its useful life. And so, for example, on the Girls of Steel, we typically retire our batteries from, you know, the competition set when this number gets up around 19 or 20 milliohms, right? So this is 0.016 ohms, which is the same as 16 milliohms. So, you know, once this gets up to 19 or 20 ohms, this battery gets shifted out, it becomes a practice battery, and we don't want to trust it in the competition. So that's the first thing, is look at that, and that resistance as it gets higher, the battery is not as good. But now that we know a little bit about Ohm's law, we can understand why that's true. And so this circuit right here shows you now, this is my 12-volt ideal battery. This is the effect of that internal resistance. So that internal resistance is like a little resistor between the battery and the load, which in our case is the robot, right? So the robot is here, you know, it's doing its thing. It's sucking whatever current it can get, and it pulls it out of this battery. No matter how much current the robot sucks, the voltage across the ideal part of the battery is always going to be 12. But what happens is we're pulling current through this resistor. And of course, by Ohm's law, that means there must be also a voltage across that resistor, right? V equals I times R. So the robot's drawing its current. The current's going through the resistor. There's a voltage generated across that resistor. That voltage shows up as a drop, right? So there will be, if there's 12 volts over here, there will be less than 12 volts over here because I lost some voltage in this internal resistance, right? And so we can work out sort of a simple mathematical example here. You know, if R int is 30 ohms, which is pretty high, right? This is not a great battery. When the robot is drawing 100 amps, which is a pretty big draw, but this is not that unusual of amount of current to draw with a robot. So if their internal resistance is 30 milliohms, you're drawing 100 amps, you do the math, you do the math, and what you see, let me move my pictures are in the way. You do the math, and what you see is that, oh, whoops, I went one slide. I switched. How do I get to the next slide? There we go. Okay. So so you do the math, and what you see is that the voltage across that internal resistor is going to be the value of the internal resistor, 30 milliohms, times the current going through that resistor, which is 100. So that's 3 volts. And so what that means up here is I'm losing 3 volts across this resistor, which means the voltage that the robot sees is 12 minus 3, which is only 9 volts. Okay, and so even though this is a full, you know, the battery is fully charged, if you put a voltmeter on it, it'll tell you it's 12 volts. When you draw current through that battery, you lose 3 volts in the internal resistance, right? And as you probably know, 9 volts starts to get into the range where you're in danger of browning your robot out, right? So everything goes down, the radio reboots, whatever, bad things happen. Okay, so this is why we don't want to use batteries that have high internal resistance in competition, because when you draw a lot of current, it sucks the voltage down, and as a result, bad things can happen. So are there any questions about that? The effect of the internal resistor. All right. Tim, you better work faster on those slides here. We're so let's see.
Or I could ask a question. So Animar came out with this load tester.
Oh yeah.
Why would I use a load tester over the battery beak?
You know, that's a good question, and I don't fully have the answer to it. You can sort of see in this picture what the battery beak does, right? It's actually measuring, so we can analyze these numbers, and it's measuring the voltage across the 2 battery terminals at different current levels. And so, you know, at 0 amps, meaning it's not drawing any current at all, you get 13.5 volts. If you pull 1 amp off the battery, you get this 13.48. If you pull 10 amps, you get this 13.2. So the more amps you draw, you see that voltage come down. Now, what I'm guessing, and Tim, you must know the answer because I know you've looked at this thing. I'm guessing that load analyzer looks at at many more points in this sort of current curve, and also can draw more current than this thing does, right? That load analyzer has got a big fan on it, so it can draw a lot of current and dissipate a lot of heat, whereas this thing, this tiny little circuit, it can only draw 10 amps. Does it do more than that?
This is a little bit more, but it's testing it under a load like you would actually see inside of a match. So then it's verifying what the amp hours are, and you can compare that amp hour rating that it gives you to the rating that you would get from factory, right? So from factory, they haven't, I think the standard battery has 18 amp hours.
So does that thing actually drain the battery all the way down until it's, okay, so it runs it through a full cycle, right? Whereas the beak is just kind of looking for a few seconds and doing this quick analysis.
So somebody has a good question in chat. So I know what amps are, but what are amp hours?
Oh yeah. Well, the question almost answers itself, because an amp is current, obviously. Amp hour is power. So it's basically a current applied for an amount of time. It's battery capacity, right? So if you hook up your battery to something that's going to draw 1 amp, and it's a 1 amp hour battery, that will last for 1 hour before the battery wears out, right? If you hook up your 1 amp hour battery to something that draws half an amp, then it will last for 2 hours. So it's just a measure of the total battery capacity. Great question. All right, so the real reason, like, you know, I wanted to talk about, I hear a lot of questions about internal resistance, so I want to talk about that. But the real reason relative to what we're talking about today is, now that we understand that little analysis about the internal resistance, we can talk about what happens when you have bad crimps or bad connections. So, you know, you can imagine this setup here where I've got my battery with its resistance, but then I didn't do such a great job of crimping the terminal on coming off of that battery, right? So either maybe the connection to it is loose, where you screw the wire onto the battery terminal, or maybe the crimp going into the power pole is bad, or maybe the connection going into the PDP is bad. The way that bad connection will sometimes show up is as a very small resistor, right? If it's a good connection, there will be 0 resistance across that connection. But if it's bad, if it's not quite making contact, or if it's making contact with just a little bit of the metal, the resistance will be higher. And so in that case, what you know, the way you might model that circuit is my perfect battery, my internal resistance in the battery, and then a little resistor associated with that bad crimp. And so you can do the same kind of math. Same kind of thing is going to happen. The robot's going to be drawing whatever current it's drawing, and you're still going to have the voltage drop across the internal resistor, which you can't really do anything about that. But now you've added this new voltage drop across the crimp, right? And so, you know, and those bad crimps will typically have much larger equivalent resistances than you get like a good internal resistance on a battery. So those can be pretty substantial, right? So here's just an example down here where I have these 2 resistors. You know, this is a good battery. It's 16 milliamps internal resistance. I'm saying your crimp resistance is like 50 milliohms. And, you know, I do this math, 12 minus 16 times 50, I'm assuming 50 amps current drawn. That's the voltage lost across the internal resistor. That's the voltage lost across the crimp. Again, I find myself, even though it's a good battery, and this is a moderate robot load at 50 amps, I found myself down in brownout territory again. So crimps can be very bad. Bad crimps can be very bad for this reason, right? And when I'm using the word crimp here, I mean any kind of connection, whether whether you're doing something with a crimp, or whether it's soldered, you know, or whether it's a Wago, or whatever your connecting technique is, or whether it's a bolt and a screw. If it's not done right, you're going to add this extra resistance, and that can cause a voltage drop, which ultimately results in you not being able to deliver as much power as you want to. Another way to think about this, and so we go back over here down into sort of a revisit of Ohm's law, right? So the next equation you would learn after you learn V equals I times R is you would learn that P equals I times V. So this is the power, the electrical power, you know, flowing through a resistor is equal to the voltage across that resistor times the current flowing through the resistor. And of course, you can use the V equals I times R relationship to go in here and plug in I times R for V, and that means the power through a resistor is also given by I squared R. So if you know what the current going through the resistor is, I, and you square it, you multiply it by the resistor, that tells you how much power is being lost. So in this example here, where my current was 50 amps and my crimp was 50 milliohms, what I see is that my power lost in that crimp, just that little tiny place where there was a bad connection, is 125 watts, right? So 125 watts is a lot of power. And where is that power going? Can anyone tell me where that power goes? You can guess. Tim's got his hand up.
Did Nobody answered in the thing.
No, I don't think
Nobody
so.
answered it even in chat. Man, it goes into heat.
That's right. That's right. It heats up. It's just like an electrical soldering iron is basically just pumping current through a resistor and heating up an element. So what'll happen is this bad crimp spot will heat up. And so that's a way, one way you can kind of diagnose bad crimps is, if there's a place where you made a crimp or any other kind of connection and you notice it getting really hot, that's a sign that you should suspect that maybe that crimp wasn't put together quite correctly. I've got a note here about telling a story about FAYUA. So, FAYUA is this summer camp. We actually haven't run it in a few years, but it's a summer camp. We sort of a first robotics boot camp where we would bring in a bunch of students, high school students from China, have them come live on campus at CMU for a couple of weeks. They'd build an FRC robot in 2 weeks and then go compete at whatever off-season event was right after that. Sometimes WV Rocks, sometimes the Steel City Showdown. And so one time at WV Rocks, they were having this problem where their robot was browning out and we couldn't figure out why. And eventually we traced it down to the place where the wire goes into the PDP was getting hot. And as soon as we noticed that it was getting hot there, then I knew what the problem was, but it took them a while to get to that point. We took the cover off where the PDP, where that wire goes into the PDP. I don't know if you guys are familiar with it, but the two wires go in, there's a cover there, you can take it off with a screw. We took it off and it had gotten so hot. So first of all, that screw, they had taken it apart and put it back together and not done it quite right. And it had gotten so hot that it actually melted the plastic there at the PDP. So what was happening was that bad place where the screw wasn't quite tight enough was effectively creating a resistance. That resistance was dumping a lot of the battery power into heat right there at the PDP. It wasn't getting to the robot. The voltage was dropping and the robot was browning out as a result, right? So these kinds of problems, they're really insidious because you can't necessarily see them unless the robot is drawing current. And most of the time, if you're at the robot and you're poking stuff with a voltmeter to check how things are going, by definition, you're not dumping lots of current into the robot because it's dangerous to be touching the robot when that's happening. So these kinds of things are really insidious because the effect of it doesn't happen until the robot's driving around at high load, and you just notice, oh, there's this brownout, and it can be really hard to track down. But this is kind of the theory behind it. All right. The other thing I'd say is that I'm giving this example in terms of a battery powering the robot, and that's a particularly bad place to have a bad crimp. But this same effect will happen anywhere. Anywhere you make a connection on the robot, if you don't do it correctly, you are effectively adding a resistor where that connection should be. And so this idea of losing voltage is going to happen anywhere there's a bad crimp. And so if it's in a bad power pole connector, in the power supply going to a motor controller, or in a bad power pole connector in the control wires going from motor controller to the motor itself, anywhere in there, you can lose power and bad things can happen again. And you can tell that by those connectors will heat up, and if they heat up a lot, that's a sign of a problem. All right, any questions about that? Okay. Next up, I want to shift into talking a little bit about the theory behind the CAN network and how it works and why it is the way it is. There's a couple things about it that are just a little strange. A lot of this, and I'll just tell you up front, is way beyond the scope of what we can talk about in this setting, because it gets into some pretty advanced electromagnetic theory. But I'm going to try to boil it down to the basic ideas and give you enough of a framework to think about how these things work. So the way a CAN network is connected, most of you have seen this, but there's a twisted pair. Our robots, usually the twisted pair is a yellow wire and a green wire. In this picture, they're blue and red, but whatever. So you have this twisted pair. It's carrying the signal. One's called high, one's called low. We connect the the Robo-Rio on one end of this CAN wire. And the Robo-Rio actually does two things. Hey, how's it going? Thank you. All right. The Robo-Rio actually does two things. The first is it's a node in itself, right? It's connected to the CAN wire. It's reading information that's being sent over the CAN bus. So, you know, this is kind of the brains of the Robo-Rio. The other thing is the Robo-Rio has a terminating resistor in it. So it actually serves as the end of the CAN bus. Okay, we'll talk about why that terminating resistor is important in a little bit here. On the CAN bus itself, we've got all these devices that are hanging off of the CAN bus, and they're connected in such a way that they should have minimal impact on the CAN bus itself, right? They're on there. If you were to model this as a resistor, you would want that resistor to be very, very high, like tens of mega ohms, so that it has no effect on the CAN bus itself. It's just kind of sitting there sniffing the voltage and measuring the signals coming by, right? And so, you know, this would be like a motor controller, or, you know, the pigeon accelerometer thing. Any device that's on the CAN bus along the way falls into this category. And then at the other end of the CAN bus, we hook it up. Normally, you hook it up to the PDP, and really the only reason to hook it up to the PDP is because there's a 120 ohm resistor there, and it terminates it, right? So this is the kind of topology we normally look at. It's just this straight line, terminate on either end, normally with a Robo-Rio on one end, PDP on the other. Okay, so let's talk about what's so special about the CAN bus and why it's the way it is. It's tempting to just think of it as two wires with a voltage across them, and that's the signal. It's kind of like that on one level, but really there's like a whole nother level of what's going on here. So the first thing is that those two wires, neither one of them is grounded. And what they do is they kind of send half the signal on the high wire, and they send the other half the signal on the low wire. And so what the receivers are actually doing is looking at those two wires and looking at the difference between the two signals. Okay, and this makes the signal a little bit more robust to noise. It also makes it possible to make a thing you connect to those two wires that really don't impact the wires themselves at all. Right, so that's the first thing, is there's this differential signal. Second thing about those wires, and this is the one where it starts to get particularly relevant to us tonight, is the wires are a twisted pair, right? They're not just twisted together for convenience so that they stick together. There's actually physical reasons why those things need to be twisted together. And some of those are simple to understand, some of them are very complicated. The simple one to understand is that when you twist the wires together, that inherently keeps the wires sort of a fixed distance apart from one another, right? So instead of just having two wires wandering around in space, you have these two wires, and the distance between the two wires at any given point is roughly the same along the whole run of the wire. And so what that does, having the wires a fixed distance apart, is it turns these two wires into what we call a transmission line. Okay, and all of a sudden you're in a different realm of electronics. Instead of having a signal that's just a voltage on the wire, what you're actually doing is you're generating an electromagnetic field in between those two wires, and you're propagating signals down in between those two wires as electromagnetic waves. Now this gets like, you know, this is like a 3-series college class in electrical engineering to really understand exactly what that means. But just think of it like sending waves down a tube, right? We're sending waves down this wire, and that has some really important effects. The big thing it allows us to do is, you know, sending the waves down the tube is more efficient and can be done faster than just controlling regular voltages. So the fact it turns into a transmission line makes things, you know, really fast, and you can have these high bandwidth communications. And then the final thing of that twisted pair is it rejects external disturbances. And so a lot of times what will happen is, you know, a thing that is emitting an electric field will basically raise the voltage of things around it. So here, you know, you can sort of imagine, here's a thing emitting an electrical field, right? And what that thing is going to do, if the field is strong enough, is it'll raise the voltage in the blue wire by 5 volts because the blue wire is closer. And it will raise the voltage in the gray wire by 3 volts because it's a little bit further away. And so when I look at the difference between these two wires, I'm going to see a difference of, I don't know why it says +8. That doesn't make any sense at all. I stole this graphic off the internet. I'm going to see a difference of 2 volts here if I look at the difference between these two, right? Because I've got a disturbance of 5 here, disturbance of 3 here. And when I look at the difference, I see that difference, right? So the radiation had an effect. In the twisted pair, what happens is, because you're weaving this wire around itself, part of the wire, part of the yellow wire is going to be closer to the disturbance and then further away from it, and then closer and further away. And the other part, the green wire, is going to be closer and further away and closer and further away. So on average, even though the disturbance is still raising the voltage in this wire, the way it's doing it, it's like raising it by 3 here and by 5 here and by 3 here and by 5 here. And it's doing the opposite thing to the other one. So when I take the difference, I wind up with no difference to the disturbance. So that twisted pair nature actually rejects external disturbances. And that's another key part of the CAN wire. When you're in a robot, especially and you're drawing huge currents with these motors, there's all kinds of electromagnetic stuff going on around that robot. So having this twisted pair helps you not corrupt your signals as a result. All right, any questions about that?
George, we've got 3 questions in the chat right now.
Oh, excellent. Thanks, Tom. Let's see. If you're crimped correctly, what would the difference between an incorrect crimp? If you crimped it correctly, what would be the difference between an incorrect crimp and a correct crimp? Well, I mean, the first thing is that it's not crimped correctly if it's an incorrect crimp.
I will go over all sorts of incorrect crimps.
Yeah. Tim, but I guess, an incorrect crimp would be basically like if you were not supposed to crimp down on the insulation and you did, and so you didn't get as much contact between the conductors as you wanted to, or if you didn't crimp on all of the strands in the wire, so you didn't get the full electrical connection you're looking there. Those would be examples of incorrect crimps that might add resistance to the system.
So Ava could clarify, but I read that as what would be the difference in internal resistance.
Who knows?
That's really hard to measure.
Yeah, and that that's actually part of what can be insidious about these, is because an imperfect crimp actually may not show this resistance drop all the time, or it may not show it at all. And you just have to be. There's a limit to what you can control in these circuits. There's some magic that's going to happen, and so you just have to make everything perfect, because you can get away with sloppy stuff sometimes, but you can't really tell when you can and can't get away with it. Sean asks if there's a perfect crimp. There's really no perfect crimp, but you can achieve a crimp that is as conductive as the conductor itself, right? So even a piece of copper wire has resistance all along it, and you're losing, there's I²R losses happening in the copper wire itself. But a perfect crimp would basically not make that resistance any higher. And so theoretically, what would happen if you wired your robot using a CAN bus that wasn't twisted? So theoretically, it would be more susceptible to external sources of radiation, right? So those transmission wires would pick up noise from your robot, and that might corrupt the signals and might cause problems. Again, this is all insidious because I can't say with 100% certainty that it won't work. And in fact, it probably will work 98% of the time. It's just that 2% when it doesn't work, you're not going to know what's going on. And then the second thing is that if you don't keep them the fixed distance apart, so they're not a transmission line, you would lose the sort of higher bandwidth end of your transmission capability. Again, it's not a cut and dry. It's not like it's all of a sudden not going to work. It's just that the higher frequency components of the signals that are going down those wires are going to get damped out, get attenuated more than lower frequency components, and that may or may not cause issues. Okay, and so the best thing you can do is try to keep as much of the twist in the wire as possible, and then let's talk about the terminating resistor. And so remember, because we got a twisted pair and the wires are a constant distance, we're using them as a transmission line. instead of like just voltage and current, we're actually thinking about electromagnetic waves traveling down this wire. And so what happens, maybe I'll just play this video. Whoop. Let me get out of this. I think I have to probably share a different screen, maybe, I don't know. Let's try and do this on a laptop. It's so hard. Where are my buttons? Here we go. Let's watch this video. So let's skip the ad. How long is the ad? Okay, so what's going on here? This is, you've probably all seen this experiment before. This person has a rope and they just send a wave down the rope. Okay, and in this particular case, the rope is fixed at the end. And so the wave bounces back and it inverts itself on the way back. Now here he's set up a similar a situation where the rope is kind of ended by a really thin rope at the end, so it's effectively free. And you'll notice that it's still, so here he's back to the fixed case, right? So the wave inverts itself and reflects back. And then when he goes to the open case, let's see in a second. So this is still it reflecting back. And now this is the non-fixed case, right? So the end can move back and forth, and you can see it still reflects itself. It just does it in a different way, right? So instead of inverting the wave, it reflects back without being inverted, right? Okay, so and this is, you've all played with ropes. You know how this works. You can send waves down a rope. Okay, so what I'm telling you is that, how do I get out of full screen? What I'm telling you, and you just kind of have to take this on a little bit of an element of faith, is that the electromagnetic waves that are propagating down the transmission line are just like that mechanical wave that's propagating down the rope. And in fact, the equations are the same. And if you really got into it, they really are the same thing. This isn't just an analogy. They really are the same thing. Now, you need a lot of theoretical physics to understand that, but it's true. Okay, so what happens in that, this little purple pulse here represents, 1 bit in the signal that's being sent down the line, the transmission line. And if it hits that open circuit, okay, that open circuit is like the open connection on the rope where the rope could go back and forth. And so what's going to happen is that pulse is going to hit the end and it's going to reflect back. And it's going to start going the other direction on the transmission line. And of course, these other pulses are still coming because you got a whole string of these pulses. And so when they hit each other, they're going to add together and it's going to cause problems. So that's what happens if you leave those 2 wires open. Okay, if you were to short those 2 wires together, that's equivalent to the case where you have the end of the rope fixed, right? So in that case, the pulse is going to hit the end, it's going to invert itself and still reflect back, and you're still going to have this weird effect happening at the end. So this is an open circuit, this is a short circuit, they will both reflect the wave. If you instead put a resistance in here, there is a right value of the resistance where the value of the resistance matches the characteristic impedance of this transmission line, right? Characteristic impedance, it's a big word, I get it. But every transmission line has this property, which is called characteristic impedance. And it's sort of like a property that tells you how the transmission line resists the wave going down the line. And so if you put the right characteristic, if you put a resistor that matches the characteristic impedance at the end of the line, what happens is the pulse gets down there, it hits that characteristic impedance, and all of the energy from the pulse is absorbed in that resistor and it doesn't reflect, okay? And so this is what's going on with those 2 terminating resistors in the CAN bus. They are at the ends and they're basically preventing these reflections. You know, this is a little picture of what actually happens. Like if you could hook up an oscilloscope to your CAN bus and look at it with it terminated and not terminated, this is what you'd see, right? If you're sending a square pulse, the unterminated one has this kind of ringing every time there's a sharp edge because there's these reflections, right? The pulse hit the edge, it bounced back, and for a little while it was reflecting, you had this kind of interference that caused this ringing effect. And then when it was properly terminated, that ringing effect is almost gone. Okay, so again, this isn't a black and white thing, right? If you like, you still might be able to interpret this signal even if it has a little bit of ringing on it, but it adds uncertainty, and you know, maybe it works 90% of the time, but when it doesn't work, it creates problems for you. So that's why that terminating resistor has to be there. All right, and so why do I think you need to understand things at this level? Well, first, before I go on, are there any questions about this? Okay, so for today's purposes, the reason you need to understand things is because a bad crimp or a bad connection or whatever anywhere in this transmission line is going to be seen as an impedance mismatch, right? So if I go back to this picture, okay, when it's open, there's a reflection. When it's short, there's a reflection. When there's an impedance, when there's a resistor that matches the right impedance, there's no reflection. But if I put a wrong resistor here, there would be still a reflection. It wouldn't be as big as these other two cases, but it would still be there, right? So when you make a bad crimp in your CAN bus, basically you're adding a resistor there. That's going to add an impedance mismatch, and that adds the potential for, you know, more spurious reflections that go on, right? And again, this is really insidious because it's hard to test for. Like you can't really tell what's going on. If you have a really expensive oscilloscope, maybe you can get in there and look at it while it's operating. Otherwise, you're just going to have no idea what's going on, right? So it's really important on the CAN bus to make your connections perfect and to minimize the number of them. And then back to the previous slide, to keep the pair twisted as well as you can. All right, any questions about that? Okay, so hopefully you understand a couple of the fundamental physical things going on underneath these electronics that drive us towards the need to really be careful when we're making connections and putting things together. Okay, and so what I've done now, this is kind of my list of, you know, how I think we should wire robots. Now I'm gonna, you know, full disclosure, this list is new. We've never actually made I've never actually made an FRC robot like this before. You know, these are sort of tips and tricks that I picked up over building my research robots. And so I think this is a good way to do it. You know, part of the reason to run this workshop is to test it out and try it and see if we want to add things to it or if there's things on here that don't make any sense. But this is what I'm suggesting as a list of standard best practices for FRC robots. Of course, you should adapt these to whatever your team does, but I think they're good fundamental principles here. So the first thing is every wire should be supported at every point along its run by mechanical structure, right? So you shouldn't run wires across gaps. You shouldn't have flops of wire that aren't supported that can move around, right? You want to control where the wire is as much as you can down the length of the run. All wires should be the right length. You shouldn't use wires that are too long and then bunch them up and try to just get them out of the way. You shouldn't use wires that are too short and force you either to cut corners or have like tension on the connector while it's connected. Those things are bad. You know, wires should be tied down at regular intervals. There shouldn't be any excess splices, right? And this gets really tempting, like in the CAN bus, you need it to be a little bit longer. It's really tempting to just add a little short piece to make it a little bit longer. What you should do in that case is take the whole run out and replace it with a single piece that's the whole length. You know, you really got to make every connection perfect. And, you know, we're not really going to go into here tonight what connection methodologies you should use, but there's all kinds of them. You can solder, you can crimp, you can use locking Molex connectors, you can, you know, there's all different kinds of things you can do, but whatever it is, you got to do it perfect. And perfect doesn't mean, what you think is good or what I think is good. Like Tim will talk about them. There are, decades of professionals have worked out standards, and they can tell you whether it's good or not, and you can look at those standards. So we want to make every crimp perfect. A key point of getting a perfect crimp or getting a good crimp or any kind of connection is to strip the right length of insulation off the end of the wire. If it's too long, it's going to cause problems. If it's too short, it's going to cause problems. This is more an organizational thing, but wires should be traceable end to end. We should label the wires at both ends, so it's really easy to tell, because if you have to take something apart for testing and put it back together, you want to be able to do it quickly. This one is a little more optional, but I think robots should be designed modularly, and that every subsystem should be easily removable, and that means the electronics associated with the subsystem should be easily disconnectable. And I sort of throw out as a benchmark, you should be able to unhook it in under a minute and reconnect it in under a minute, so that if you need to take that part off because it broke during a match and you've got a spare in your pit and you want to put it back on, the electrical part of that job will be under 2 minutes. And hopefully the mechanical part of the job is quick as well. I think, and this is something that comes from the Girls of Steel experience. After this year, I feel very strongly about co-locating the sparks with the motors, because running those encoder wires is a nightmare. And running those, making extensions for the 3 conductor brushless motor wires, also a nightmare. So you can avoid that by putting the spark next to the motor. That means you have to design and lay out your board in a fundamentally different way, but I think it's worth it. All the status lights should be easily visible, right? Those status lights are there for a reason. They're really useful to look at to see what's going on. Girls of Steel this year, we had this e-board. It was nice in the back, you could see everything. And then we put a sponsor panel with a bunch of stickers over it, and we couldn't see any of the lights anymore. So make it so those lights are visible. Keep that in mind while you're building things. All connectors should be locking. You don't want to leave it up to just friction to hold your wires together. So you should have positive connection. Either there's a locking connector, or you zip tie it together, or you've got some other kind of mechanical strain relief holding that connector together so it doesn't just come apart on you. And anytime you pass a wire through metal, you drill a hole in the metal, you pass a wire through, that hole should be deburred, and you should put a grommet in it. So, grommet's like a little rubber washer that goes on the inside of a hole so that you don't abrade the wires when they go through.
So George,
yep, go ahead, Tim.
George, do you want to jump over to my slides before we jump into the Gauss wiring real quick?
Yeah, sure. Is that at the end?
I will jump on to it.
Oh, yeah.
Made a totally different deck because we can't share out my deck entirely.
Yep,
unfortunately. Gotcha.
Oh, wait, I see a question from Anuva. Is the unterminated cable graph for the open or shorted circuit? Did I answer that in my general talking, Anuva?
I don't think so. If you did, I missed it.
Okay, so the shorted case is equivalent to the case where the robot is fixed where the rope is fixed at the end. The open case is equivalent to the case where the rope is free at the end. Is that what you're asking?
I meant about like the graphs. There were 3 types of circuits that you showed, and then there were 2 graphs. One was like for untethered or unterminated, and the other was for terminated.
Oh, sorry. Yeah. So that was, the terminated was properly terminated with a resistor. The unterminated was open. So I didn't show one with it shorted together. There's other problems that happen when you short the end together, because you lose low frequency response in your transmission line. So it gets a little trickier. Yeah. So those 2 plots, the one with the ringing was with the unterminated, no terminated resistance at the end, and the other one was with it matched.
So does that mean that like there would be no consistent graph for a shorted circuit, or does that just mean that the shorted circuit looks strange or different?
So the shorted circuit would it would look the same if you were using high enough frequency pulses, right? So I can't remember, I just grabbed that picture off of, but the width of those square pulses matter. And so it would, we can talk more about it offline, but you know, if you short the end together, the high frequency parts can still do the normal thing, but the low frequency parts will go away.
Okay, cool. Thanks.
So I'm here to talk about real like standards, right? So George covered some theory, right? And now I want to talk about standards, right? There are a myriad of different ways that you can do certain things on your robot, right? Whether you're using Wagos or Andersons or you're soldering, all of those things are kind of up to the teams. But the big one is that for each one of those, there is a right way and a correct way of doing it. George made a great list of recommended best practices. This is kind of from his experience. The interesting thing is that a lot of those best practices that he talks about are also right in the IPC. So the IPC is a international printed circuit board organization, but now just shortened up to IPC. They work with another organization called the Wire Harness Manufacturing Associations. And so they developed this whole set of standards. And so I went through all of this training for the RI so that we could finish building robots that go to space. And then also so that I can teach students at the RI proper wiring and harness stuff. So in this presentation, you'll hear, or if you read the standard, you'll hear about different classes, class 1, class 2, class 3. Class 1 items are just general run-of-the-mill electronics that it doesn't matter if they ever fail, okay? Class 2 is a dedicated service electronic product, meaning that it's a touch screen, it might be a laptop, right? It needs to have a high duration and the use case needs to be uninterrupted, right? But if it fails, life isn't on the line, okay? Now, class 3 stuff is a life is generally on the line and equipment downtime cannot be tolerated for any reason, right? So we're looking at continued high performance in these situations. Now, you could argue on this that, you know, well, we're just high school students building robots, right? But at the end of the day, we don't want any of our robots to be dead on the field for an electrical issue that we can avoid. So the way that I view most of our work on the Titans when it comes to electronics is that we are wiring a class 3 device. And therefore I expect a class 3 standard with the terminations, with the crimps, with all of these things. So that's the way that I inspect it. Now I let some stuff go because you're high school students that are just learning, but I still try to hold a very high standard. Now, there's a way that the IPC evaluates stuff that's acceptable, which is not perfect, but integrity and reliability of the item is maintained. They used to have a target zone where it was the perfect item. But the issue was people were refusing items that were acceptable, but were not the perfect target. A defect means that it's unacceptable. This doesn't allow the item to work as designed. So this would be a bad crimp, right? A bad solder joint. And then we have a process indicator. This is a close to a defect, but it's still acceptable. And we need to just watch or teach the student a little bit different so that they don't devolve that process into a defect. Okay, now let's talk about wire real quick, right? So wire diameter is pretty important throughout all of this. We have a conductor diameter and a wire diameter. The wire diameter is the outside of the wire around the insulation, okay? And then the conductor diameter is the diameter of the conductor underneath with no insulation. This gets kind of tricky when it comes to some of our crimps and gauges and stuff like that. But this is something to be aware of, that depending on when you're looking at a data sheet for different items, they might be talking about conductor diameters and they might be talking about wire diameters. Now, inside of this, there's also a way that we inspect items. Okay, for the majority of the items that we're doing in FRC land, we're dealing with wire gauges that are larger than 14 gauge. Now, for any of you who are not familiar with wire gauges, the larger the number, the tinier the wire. So the battery wire, when we hook up the battery from the battery to the PDP, that has to be a minimum of 6 gauge wire. And then when we wire up Falcon motors or other stuff, we're looking at a 12 gauge wire there. 14 and 18 are used for some smaller motors and other systems. And then our CAN bus is in that 22 range. So we're looking, when we inspect these items, at either no additional magnification needed or only up to about a 3x. The referee is if you are a big client, you're trying to, you know, accept or refuse an item. Now, let's talk about some damage that goes on to the insulation of our wire. And so on this, we have a nicked insulation up at the top. You can see that that's like somebody started to crimp something and then they said, hey, nope, I'm not going to do it. Melted insulation. This happens a lot with a heat stripper, which no FRC teams use, as well as the charred also happens a lot with heat strippers. This reduced is, you know, a soldering iron or something else bumped into it while you were doing some work. And the ragged insulation is just that you have this, you know, piece that was left over because you grabbed really dull wire strippers. And so what this has is this insulation shall not have cuts, breaks, cracks, or splits, period. Right? It shall not be melted, right? It shall not have a thickness reduced by more than 20%. That would be like if you took 12 gauge wire and you used 18 gauge strippers onto it. It would cut that outer jacket or outer ring of insulation. Can't have any of that stuff, right? Shall not have ragged pieces of insulation greater than 50% of the insulation diameter or 1 millimeter, whichever is there. So these are things that the whole industry of people that are in wiring have said, none of this is acceptable. So I would encourage you to take that same exact approach for your FRC wiring, right? They also talk about strand damage on this. So this is, you've stripped off this wire, it's kind of floated around your shop a little bit, and this is what's happening, right? So you can see down here, it's a little bit tough, but you can see some strands that are cut off of that. Again, that would be caused by somebody not using the correct gauge of stripper. You can see some bird caging. This is that lay of the wire, the nice twist that comes with the wire is all messed up. You can reestablish that by just twisting with your hands, but if you're not reestablishing it, it also counts as a defect, right? So they have in this presentation, because I kind of pulled this straight from the IPC stuff so that it adds a little bit more credibility that it's not just Tim and George making this stuff up, right? They have a whole bunch of tables and additional images that really do this. A nice one that I've seen a fair amount with FRC is strands shall not be cut to fit. What this means is, oh man, I have this connector right here and I need to get it to fit, but it won't fit in. So I'm going to take that 12 gauge wire, I'll go 18 and I'll cut it all the way around so it fits into my 12 gauge terminal. That's not acceptable. That's going to cause an issue for you. Okay. Now, there's certain things in FRC land or in wiring land where we tin the wire. And I'll tell you what the tin wire is supposed to do and how it works. And then also where we don't tin that wire. Tinning of the wire is where we add additional solder to everything, okay? And I have a nice video that shows what tinning looks like. But if you are crimping wire, okay, and almost all the wire that we deal with in First Robotics is what's called stranded wire. It's not solid. If you went into your house and you opened up the wall, I highly don't recommend it. It's 120 volts AC. It will hurt you. It's not forgiving like FRC wiring or robot wiring is. You would see what's called solid wire. So what we deal with First Robotics is a stranded wire. For stranded wires, we are tinning them when we do a splice or use a solder sleeve. When we crimp the wire, we are not tinning it. When we are using it underneath a fastener, we're also not tinning it. That one might be surprising to some. And if we do a mesh splice, we're also not tinning it. Okay. Now, when we tin wires, we have a couple defects. Wicking, where it goes way too far up. Wetting, where it's just too much. Okay. It doesn't penetrate the whole way. Non-wetting is the non-penetration. And then a buildup. Now, let's talk about wire strippers real quick. And I'm going to play a video for you of wire strippers. Why is this not? There we go. So you can see this is a nice set of wire strippers. They're IDing the item based on the gauge. They're then taking and they're breaking this. Now this is the proper way of stripping the wire. They broke this. Now what most people do is they grab their wire strippers, they grab their wire and they pull it off the entire way. Now what the proper way of doing is, you'll see this right here. They score it, they break it, and now as they're pulling it off, the extra insulation, notice how the operator is twisting the wire. That's the nice, good way. That still establishes that lay and prevents any bird caging from happening. So this is using a different style of stripper. This is a kind of an automatic stripper, but you can see what happens right there is, again, they use it to split, and then they are taking and twisting it the whole way out. A lot of students really like the automatic stripper, and they think that it's supposed to pull off all of the wire for you, or all of the insulation off of the wire, because a lot of times the connectors that we use in First have a very short strip length. That's not the case. So I highly recommend this style of mechanical wire stripper with the single jaw for most of your work in First Robotics. Now, this is tinning of wire, and so this is the preparation of it. We have a nice smooth coating of solder, is how it's supposed to look like, and we're supposed to be able to see and identify the individual strands of wire underneath here. A defect that's happening here is that you can see with this that there's not wetting that is happening, meaning that it's bare wire right here and only a couple places are soldered. Here's another defect where you can see that it's tinned and then there's this big solder buildup or icicle that's kind of happening. A lot of times that'll happen towards the tip as well, but we're looking for this area right over here. And so here's a great little video of us taking and tinning the wire. So you notice that what they do is they start off, they have the solder on the soldering iron. They're now holding that wire and they're just flowing that evenly right in. At the tail end, they just wick that right off. So let's play that one more time for you. So this is quite literally how tinning of wire works, and it's super, super easy after you practice it about 400 times. So right there. And that's how it should look. You can see the individual strands of that wire there. So another option for you is to use these heat shrinkable devices if you're doing a splice on wiring. When you do these, you have to overlap the wire at least 3 conductor diameters. That's the diameter not with the insulation. That's the actual wire there. And they need to be properly parallel. You have the solder ring in these, and this is just a meltable item. So you're not actually doing soldering. It has this meltable solder disc in there that when you heat it with a heat gun works out great. If you don't have your heat gun hot, you can actually char this, or if you have it too hot, you will char it. So we're looking for this nice setup here. And we put this stuff in parallel. So there's a lot of these items where you're looking at the sleeve is not burned or charred. Discoloration is not prevent. The nice thing is right back here is the conductor contour is still discernible and the item underneath is still discernible. Okay. So that's these things are awesome for a lot of stuff. I'll share the link out to this video. A lot of you might have soldering irons in your shop. This tip maintenance for this is really important that you can do. Rashika, you ask if you mess up the tinning of the wire, is there any way to fix it? There is. Sometimes that is if you had like this, where you had no wetting of this or missing, you would just heat it up and flow enough solder in. For this solder buildup or icicle, sometimes you can heat this up and kind of move that icicle off towards the tail end and then just clip that off. One of the things that is a defect that really is not fixable is wicking. And what wicking is you have the end of the insulation right here and solder has wicked all the way up underneath that insulation. That one is almost the only one that you can't really repair on that. So, so when you do soldering, it's really important, and it's infuriating for people because people that know how to solder make it look ridiculously easy. And for most people, you're learning from somebody who knows how to solder. So then when you go in and you start soldering, you're like, oh my God, this is the hardest thing ever. Okay. Having good equipment really does matter. Okay. What this means is that the tip is actually a good, clean tip. You haven't used it to burn holes in plastic. You haven't done that in, right, doing a whole bunch of stuff that is bad for that. Okay. Having a tip that's the right size, it's a different tip if you're doing tiny electronics work versus trying to solder and tin 12 gauge wire. So whenever you buy a soldering iron, it generally comes with a variety of different tips. On FRC teams, they just like lose those for some odd reason. If you go into a proper E-lab, they're all sorted out and ready to go. And then maintaining a good temperature. Temperature varies based on whether you're using leaded solder or lead-free solder. In general, I find it to be easier to solder with leaded solder. However, that has some safety concerns onto it. And then also having proper rosin or flux around also helps out. Okay, so the tip should be about equal to the width of the joint that is being soldered in most cases. Temperature should be as low as possible to get good wetting. Typically with leaded solder, that's 650 to 700 degrees Fahrenheit. It's hotter with lead-free. Okay, there are different shapes of soldering tips. You can watch all sorts of videos on that with soldering. There's also different metal combinations with soldering. Sometimes what you're looking for is a eutectic solder that's a 70 and 30% mix. And then in most cases, you want to use a flux. Okay, you can get a rosin core solder, which makes all of your work a lot easier. That's what we use on the Titans. We use a rosin core solder, so they don't have to worry about external flux. When we do this, we touch the solder to the tip of the iron to get flux flowing through. Now, this is not a giant buildup. This is just a little buildup there. And then we apply the solder iron to one side of the connection, and then the solder to the other side. So notice we're having this going on opposite sides. After we do this, the connection is now fully heated. The solder starts to flow in, and the flux will kind of start to smoke out. That's that smoke that you see kind of flowing when you do this. So I like to have a fume extractor around, helps it out. Solder is going to go towards the iron. Solder likes to go towards heat. And then after you're done, you just remove the heat. That's pretty much it. The whole entire process takes about 3 seconds. Shorter and you're not getting good wetting. Longer and you're maybe overheating the board or burning things. Different items are going to take a little bit longer or shorter based on heat dissipation. When you're done, you should be able to see all of the elements. So this is a great picture right here of a terminal. It has a looped ring and you can actually see all the different parts. You can see the solder right here, and you can actually see the wire strands. It's not globbed on. If you're doing boards, this is all bad, right? Everything on here is just ugly. This is a sure sign that you actually don't know how to solder, and everything on here is probably going to break. Okay. I would encourage you, if you really like electronics, if you really like soldering, to practice. That's the only way to get better at it. And talk to a mentor. There's all sorts of these cool little electronic soldering projects out there that you can practice on. Wire is cheap for the most part. You can sit there and you can splice wire all day long to get used to soldering. Okay. Soldering is only one little part. For the Titans, we do almost all of our CAN bus as a soldered connection. And we use a crimped breakable connection only on devices that we know are going to have to be removed for service. So in 2022, that was all of our climbers. We knew that we were probably going to have to swap them out. But everything else on our whole entire CAN bus was all a soldered joint. Awesome. So let's talk about crimped connections, right? So on this, crimped connections, these are something that you're familiar with. These might be ring terminals, but for the most part, most people in FIRST right now would be thinking of this as an Anderson power pole connection. Okay, so we're looking at no damage to the plating or finish. That means this part right down here, the ring section, and we're not looking at altering any of these, meaning that we don't want to just take and booger this up. Like if this is not the right size for the bolt that it's going on, that doesn't mean we grab a hand drill and drill it out. Okay. Now, conductors, again, should not be cut or modified. That means that if you only have a 12 gauge or you have a 10 gauge connection here and you're trying to put 6 gauge into it, you're not cutting out any of the conductors. The conductors also should not be tinned or overly twisted to go into this. It's important that they're actually kind of straight because it's deforming and compressing all of those. Okay, and we also can't use a crimped connection on solid wire. Now, the IPC recommends that you use full cycle crimpers. That's this style. That's the style of crimper that most people are used to for Anderson power poles. Once you start crimping, you can't stop right midway through. This means that you're more likely to get a consistent equal crimp. Okay, that's for class 3. For class 1 and 2, they don't really care. But again, I treat the work that we're trying to do as a class 3, or at least aspiring to be a class 3. Okay, because I really don't want our robot to break down on the field because of a wiring issue. Now, it is also important that you look at the identification that comes with any of the crimps that you're using to find out what it is. And so we'll talk a little bit about that in the slide or two. On this, there's different components as part of the whole entire connector. What we have right here is an insulation inspection window. What's happening right here is the insulation is stopping in this area. So I shouldn't see no insulation and I shouldn't see just insulation in that area. Number 2 is the entry bell mouth. Then I have number 3 is the brush end bell mouth. That just is an area that wire is passing through. Then I have a brush inspection window. In this area, I should just be seeing a little bit of my insulation. And then I have all of the components down here, 6, 7, 8, 9, 10, that are all part of the actual crimp. Number 7 is the conductor crimp area. This is going to vary depending on what crimp you're actually using. If you're using something like a Molex crimp for the 0.1 header pins that come with PWMs or with CAN bus, it's going to vary and be different than an Anderson power pole. So that's what's happening in all of this stuff. And so this is what should be happening. Again, we should not be having any strands that are folded and outside of this. We also shouldn't be getting a ton of deformation right here. In this, what is happening is the defect that you see is that the insulation should be ending, and you should be seeing it in this insulation inspection area. And instead, it goes all the way under and is in the crimp. And so now I don't have good electrical contact between those two areas. I don't have good signal integrity, and this is going to cause a failure. Okay, with this fold back of the brush strands, what's happening there is I have something that might prevent it from locking into the housing on this one that's coming out the front. And on the back, I have something that might be causing it to short out to another connector that's right next to it. Okay, and the deformation is something that's going to cause probably a mechanical failure where that is going to break off right there and not and then cause a whole bunch of other issues. Okay, so we can see right here on this little section that's normally on the 0.01 header pins is wrapping around, and it should be retaining it. That in this situation is just not tight enough. Okay, so that's what's going on right there. So let's look at the back of these. This is something to note of this, where again, this is kind of really irregular shaped crimps with all of these. I would say that A would be over crimped, B is kind of just ugly. C, you can see is stuff is sticking out the back and not there. E right here is a filler wire within the crimp is not extended beyond the outer lug. So one of the things that I hear a lot with First Robotics and stuff is, well, the item that I'm trying to bolt this to has a bolt for a 6-gauge wire, but I don't have this, and I need to put 8-gauge wire, or I need to put 28-gauge wire into this, right? And so what happens if you need to do that is you want to actually overstrip the wire. So let me draw real quickly on the screen here. So if this is my area that I'm crimping, generally what happens is you strip enough wire so that this is your wire right here, going back, right? And you've stripped enough wire that you're just going into that crimp housing right here. Now, that generally is how you're doing it, and you want it to end. But if you need to fill up that area, what is acceptable is to overstrip and fold that wire back through. Now, in this situation, it cannot be extending out of the front right here. Okay, that's not acceptable. So what we want to do is, let's do eraser and erase those two. What we want to do is when we overstrip and we fold it back, we need to do that where, don't make me draw straight lines, where it is overstripped and folded back here. Now, this right here, this filler wire extending beyond the insulation area is actually going to be a defect for you. So you don't want that to be happening. You want that to be terminating right down in here, as close to the end as possible, but not extending out. Okay, so let's clear.
So Tim, I've done this hundreds of times. I had no idea it was kosher.
It is. It was also super surprising for me when I was in the training, George, because I was like, no way, that's actually legal. I totally thought I would get dinged for that one.
So let me ask my kludgy question. Can you fold it 3 times?
I would probably try not to. They don't talk about how much filler wire and in this. All their explanation and examples is only one time, George. So, yeah. So another way of doing this, and this is actually really, this is even better than kosher. You can see this right here. This is folded as well, George. inside of here as a filler for a machined contact. The best way of doing it is actually not the fold over. It's, you know, if you have to do one or two, fold it over. But if you have to do a lot, the best is an adapter bushing right here. And so if you ever tear apart any of the stuff that AndyMark sells for their chargers, you'll notice that it's a big Anderson power pole, like, you know, connector that you would use on batteries, but then they have a number like 10 video or a number 10 gauge wire going to the charger. Okay, what they're using there is they're using an adapter or a fill or bushing. They're not doubling that over. And so you can get this from PowerWorks, from other companies, and I highly recommend using some of those. You can also apparently this is a defect right here. Is, hey, I want to use solid filler wire for this. It is also acceptable to not fold it over and then instead just put inserted wire in there, but it is not okay if that exceeds out. Okay, the excess, when they're talking about exceeds out, they're talking about beyond 2 wire diameters here. So just a little bit of excess is okay. It's 2 wire diameters. So that's going to vary depending on whether you're using 6 gauge or 28 gauge wire. Okay. So ferrule crimps, we use a lot of these. Again, the conductor cannot exceed past that ferrule. This is exceeding right there. It also shouldn't, it should be just a little bit recessed there. So that's what you should be looking at. This is not acceptable right there. This is not acceptable. This slight recess is good. Termination ferrules, this is an over crimp right here. You can also see flattened and bent. Those are all going to be defects there. Insulation displacement connections. These are, if you ever have done like a Talon SRX ribbon cable extension, that's what this is. And so this is, you have to have the right wire, you have to have the right crimp. Way back for the old mentors on the phone call, we all would remember the digital sidecar that went with the SCRA. That was also the best example ever of an insulation displacement crimp. It's actually, you know, the Talon SRX breakout cable is kind of a rarity for this. But what this is you're not doing any stripping of the wire. You're taking a housing and you're pinching that on, and you have to pay attention to the orientation as well as the fold back. The fold back is what helps to lock this connector in, and then it also has to be flush. Let's talk about wiring labeling here. So wire labeling in the land of IPC is not required, period. It is only to the customer specifications. That being said, just about every customer requires wire labeling. And so there's a right way of doing wire labeling and a wrong way of doing wire labeling. Let's talk about some of this stuff. No matter what, regardless of the wiring method being used, it must contain the required information by the customer. That's you, the team, right? You develop your own standards. Make sure, right? And keep it consistent. If it says motor 1, do motor 1. If it says this, do this, right? If you say ABC, do ABC on all of them. Now, it must be legible and it must be permanent. Now, that permanent does not mean I just marked it with Sharpie, okay? Sharpie on insulation tends to wear off, okay? And it must not damage the product or impair its function, okay? Now, it also says prior to delivery, temporary marking shall be removed. That means that you marked it with a Sharpie or something else. Marking must remain legible after exposure and handling and testing. Now, this is a wire wraparound sleeve. This is actually a heat shrink one, super awesome. Some heat, if you have an Epson or a Ksun printer, it'll be able to print these out if you get the right cartridge for it. That's really nice, right? You can also take the regular Brother printer and print out those and wrap it around to get this. It must be legible though. All of these things all make it defects. I can't get any of the information that I want to out of this W2 or the ICD or this. None of them are actually legible for me, right? These two on this one are actually legible. Despite this having a couple wrinkles and creases, it's actually legible. Down here, where the wrinkles and creases cause it to not be legible, that's a defect. A flag marker is something like this. It takes a little bit more space, but sometimes is needed for small gauge wires, right? You just couldn't print it small enough to actually get it on some of the wires. This is acceptable, this over here. This is not. Now, sometimes it's very hard to do this, and what I'll do is if I get it better than this one, I'll just take and I'll trim this with some scissors so that I don't get this sticky overlap there. So let's talk about wire retention as well. So tie wraps, this is something that's important. Every student on my team knows that zip ties and properly cutting them is like a pet peeve of mine. It's not just a pet peeve of mine, it's a pet peeve of the whole entire industry. And they say this should be flush, period, right? It's not a like, oh, good wiring is this. It's like, nope, wiring, period. If it's not flush like that, should be a defect, all classes, right? Even the junky electronics that we don't care about, it's doing it. Now, the other thing is that the tension of this is also a thing, that you should not be over tensioning when you're using zip ties. What that means is it's actually cutting into the insulation or the bundle. It's really hard to think about it that way. You're thinking of, oh, I tighten up the zip tie as hard as I can. But really, sometimes that actually has a potential to do more damage to your wiring structure than keeping that zip tie somewhat loose. Unless otherwise specified, spot ties or tie wrap straps are spaced evenly and an increment that maintains the bundle's desired form. So 6 inches, 24 inches, this, not okay. You want 6, 6, 6, 6, maybe 8, 6 is okay. But you're trying to also keep that form going through there. When you're doing breakout cables, you should be doing a zip tie after just about every single breakout bundle right here. This item right here on this end has too far behind its zip tie or retention to do that. Now, in this image, they're using a different thing. They're not using zip ties, they're using lacing for that, which is really cool cordage. It's awesome, but it takes a while and would never be really practical for a lot of FRC students to do. When you do the breakout right here, you have the main bundle, you have a breakout, and then you have the branch right here, and then you can see the additional ones. They're not more than 3 bundle diameters from the breakout is the restraining devices in a manner that maintains the desired form and function, and they're breaking out and they're retained before and after each breakout. This is tends to look like our wire bundles in FIRST Robotics here, right? So this is on the image is what we want on the left, and what we have on the right is generally what we get, right? Is all sorts of power wires and signal wires all twisted around and just thrown in there, an inconsistent diameter the whole way through. This is classified as a defect by the industry. It generally is what we get in FRC, unfortunately. Bending radius is a thing. So the bend radius is measured along the inside of the curve of the wire or bundle. The minimum bend radius shall not be less than whichever cable in the assembly has the largest bend radius. So this means that if you are bending your number 6 gauge battery and your 12 gauge power to motors and your CAN bus all together, that the bend radius that you have is defined by the 6 gauge. If you debundle all of that, then it would be defined by the 12 gauge. This is defined in table 14.1, which you don't really get except for right here. And so 14.1 gives us the bend radiuses for all sorts of different wires that we have. Generally, all of this stuff that is up here of the coax cable, we don't care about. We do care about Ethernet cables. Those are a 4x bend radius based on the outer diameter. And then we also care right down here for most of these insulated wires, bare wire, and that's a 2x of the diameter. Okay. Sometimes we end up terminating a wire and we still need to keep that inside of our bundle. Maybe we removed a subsystem. Maybe that we're planning on adding a subsystem onto that. And so when we do that, we need to make sure that we shrink over top of that and we fold that over underneath right here. So this is a good way of doing it. This is a good way. This over on the right-hand side is not. You can notice that it's kind of just sticking out of that. Okay. Routing over splices and ferrules, it's tough because a lot of times when we put a splice in a bundle, we are increasing the diameter of that bundle and then shrinking it down. We don't want to put our zip ties over top of that splice, okay, to crush that splice or the ferrule. And we don't want to put those zip ties or retention items so close that it changes the bend radius right here. So you can see with this bottom one and this one right here, it's putting so much pressure on the wire that is exceeding that bend radius. And that's going to cause us issues when it comes to signal and everything else. And also just main power, okay? Retention, so this is a retention setup of what are we dealing with hardware when we actually bolt items down. So hardware installation, when we do this, correct parts, correct sequence of assembly, and no discernible damage. They call this out. This is in a standard. So when we're bolting items down, we want to do the exact same thing and pay attention to torque requirements and all this. There's no great pictures in the slide deck. Raceways, we use these from time to time in FRC. And what we're doing is we're bundling and containing them within a raceway, and we're securing that bundle at the entry and exit points of the raceway, and we're also needing to secure the raceway at those points, okay? So that means we're not just taking a bundle and throwing it in, we actually have a zip tie or something placed there. And then no damage or distortion inside of to the raceway. George talked about grommets. Grommets are important. There's a whole bunch of different types of grommets. For the most part in FRC, we use these rubber grommets. They don't really have an orientation to them, and they also don't seal. But we also do want to install them if you had engineering documentation to that, right? You'd have to create that. You'd have to have like an army of electrical students to create electrical documentation. That being said, when I was judging out at Worlds, I did see it. So that's my whole entire slide deck. I wanted to go over one different thing on the Anderson power pole stuff. And so that's this right here. We'll refer to this but every electrical crimp that you ever will find will have manufacturer's documentation on something. Whether that's a Wago, right? This has manufacturing documentation for the exact strip length, for the gauges that you're using it on, and gives you a bunch of different information. This is directly from DigiKey's website, which pulls it from Wago. But Anderson has a great one with PowerWorks where they show us the width of the crimp. It's 0.17 width for the AMP 50s that we get. And then we're looking at right here, the actual cross section of how this is installed. So you can see where the insulation ends. You can see where the crimp ends right here and this little tiny gap. You should never be able to see bare wire from the back of your Anderson power pole. That's not acceptable, okay? But you can also see that the crimp that's here, unlike the one that I showed in the PowerPoint, does not have something that attaches onto the insulation. You can also see that you don't see any bare wire of your conductor right in here. That's also not acceptable for an Anderson power pole. So you can see right here the correct situation on that. You can also see that there's a retention hook or a spring right here that is always in those Anderson power poles, and that latches on to the little hook. If you were to put these in incorrectly with the housing, you would notice that the crimp does not actually hold in, right? The wire would just pull out of the housing. So it's important for you to do a tug test when you have the crimp on to do that, and notice how everything is nice and symmetrical, and after you do an insertion. Okay. So this is a great little guide for that. I like doing this as well. For these, I really don't like the 221s or the Wago connectors. I think that Andersons are better in my opinion, because when an Anderson is done right, it works. It's hard to do right, but it works. These 221s are a little bit tougher to get consistently right every single time, and it's hard to verify it right. Somebody on your non-electric team comes over and they open it up because it's really easy and they then put it back together. They might not be looking for the same things that the person that is trained for the Anderson power poles would do distinctly, okay, and is inspecting for. When we do soldering on the Titans, we use a Western Union splice. So what we do is we tin the wire first, and then we twist that wire together, and we make sure that we have over 3 twists there. Sometimes if we're in a hurry, we won't tin the wire. We'll just take the wire that's twisted, we'll cross-lap that and do this, and then we'll solder the whole thing. However, when we have the time, we like to have tinned wire there. And so this one is because it does not add that much resistance to it. It also doesn't change the overall diameter from the insulation too much. And it is a mechanically super strong joint. So there's some tips and tricks and pointers and rules on all of this stuff. If you have questions, we're going to practice a lot of this stuff on the hands-on and really try to beef up those skills. George, if we want to go back over to the other slide deck, we can talk about kind of the Gauss robot and look at that, and then kind of say, here's what the plan is going forward.
And I'll do it real quick because we're over time here, but let me bring that back up. Where was it? Yeah, it's this one.
We aren't overtime. This event ends at 9:30.
Oh, is that right? Wait,
yeah.
I thought it was 7:30 to 9. Okay, so 7:30 to 9:30. You tack an extra half hour. That's good. I like it. All right, so I'll take a little more time then, but I'll still do it quick. I don't want to. I'm not here to embarrass myself and the Girls of Steel. But we did a lot of examples of some wiring that can be improved. So I want to point those things out and talk about how we're going to fix them. And like this picture right here, I would go to slideshow mode. This is just exemplary of you know, a problem that you just can't do that much about. You know, we did our best to try to manage this, but using this right here, this little ribbon cable, this is one of those encoder extension cables. Sounds like a good idea because it allows you to put all your motor controllers back at a central keyboard and still run the encoders for those brushless motors, which have to go to the encoders. The problem is those connectors are really hard to make. And so the only realistic way to do it is to buy extension cables, and they come in fixed lengths. And so what happens is you wind up with way more than you need, and you wind up with these little bundles of these cables, and they just create a lot of problems. So this is kind of the main thing we want to try to fix in the rewiring of the Girls of Steel robot. Now there are some things that I like here. You know, one is these power poles are zip tied together. Of course, Tim would complain about these not being flush cut right here, but you know, that's good. But this cabling mess is something we want to try to alleviate. This is another one, you know, and you think about that, you know, ideal of not making more connectors than you have to. Here you see there's a little 3-inch long extension cable from the, you know, so these are the 3 cables going. There's a spark up here on the e-board, and there's the motor, and this has to be the drive motor, so this one's going to get a lot of work. And they weren't quite close enough together to make this connection. So there's a short little this short little cable here, and you know, that adds basically 2 extra crimps to this run. And as you know, every crimp is a risk. So getting rid of some of those will be a good thing. So here's an example of what this is one where we did it right in the sense that we co-located the spark. However, we did it wrong in the sense that we bought this thing that sort of was made to connect to a reverse planetary gearbox, and you can barely see the spark is hanging off the bottom of this thing. So there are two problems with this positioning. One is if it's on the bottom, you can't see the lights. And so whenever we needed to diagnose this, someone would have to like set up thankfully we all carry cell phones around, right? So you'd have to like turn on your cell phone with the camera, with the face-facing camera, and stick it under the robot and leave it there, and then have someone do something so you can look at the screen and see the lights. And so that's kind of annoying. So we couldn't see the lights. The other thing is that because this is on the bottom and this is close to the floor, we had issues, even though we worked really hard to try to manage these wires down here. They're just in the way. They got caught on stuff. They got yanked out a couple of times during matches. So that's something to fix up. So here's an example of a robot that is, this is the other end of the non-collocated spark thing, right? So here's the motor. There's actually a fairly nice cable container unit. But again, this shouldn't be necessary, because if the spark was here, the only thing we'd have to do is run power out to this motor. And we'd be able to keep the CAN wire and the 3 conductor cables local. So this is one where the controller is way back in the e-board in the back of the robot. I'd like to fix that. So this was actually interesting. This was an add-on we did at the end of the season, because we added a back roller to our shooter so we could shoot high. And in this case, the sparks are co-located, which is great. That actually worked out really well. It's a dedicated auxiliary board. We actually, designed it in to mount with the limelights. That's all kind of cool. The wiring here, the execution isn't great. We're not like these wires aren't really being managed in here. They're just kind of flopping around. This one here is especially bad. Here you see the Ethernet cable. This is an example of, cutting a corner because it wasn't quite long enough. So it's kind of cutting this corner. It's like not supported across this big gap here, right? So those are kinds of things we want to fix up, right? So I don't really have a more formal design than that. So what we're going to do to this robot is the highest level bit is we're going to co-locate all the sparks. And so that means we're going to have a bunch of little auxiliary e-boards. We will be running just power to those e-boards, power and CAN to those e-boards, and then managing the encoder wire and the signal wire to the motor drive wires. We'll manage those locally. We'll just do some nice wire management. And for the CAN bus, we're going to use, now I've never used these before. The Sharp people speak highly of them. But we're going to use these locking Molex connectors for the CAN. So this gives us the advantage of being able to both have a removable connector, but also have it be lockable. And if you do the crimp right, this should be a pretty solid connector. All right. So that this is the plan. Mentors are going to do a lot of work between now and then to get us ready for that. And we'll probably be recruiting students in the lab to like cut pieces for us and stuff like that. But the idea is we'll show up on Wednesday night. I hope to see you all there, and I expect we'll spend a good amount of time just on the bench practicing. I think Tim went through all those great standards. The truth is that even once you know the right way to crimp, you still got to do it a bunch of times before you can actually get it right. And so you got to do it, and you got to visually inspect it, and you got to have Tim come over and look at it and say, oh, that window there, your insulation didn't go into the insulation window, so you got to do it again. or it poked too far out, you know. So those kinds of things, we'll practice doing some of that, and that's really valuable. I know as students, when I was a student, I wouldn't have thought of this as that exciting of a thing to do, but it's extremely valuable to get that practice, and will help you out. And we'll spend some time doing that, and then we'll move on to the robot and start adding stuff. Like I said, if you bring your own robot, we'll work on your robots too.
And at the end of this, tomorrow's the only meeting that we have scheduled, right, for this. What we'll work on, it's actually
Wednesday.
Wednesday. What we'll do on Wednesday is we're going to talk about, okay, these are the projects that y'all are getting into, and what are the nights or days that we can meet that continue to give you additional time so that you can work on this and get the work that you're committing to do done properly. Okay. So often in FIRST Robotics and the build season, we go, oh my God, the wiring has to get done, by next meeting. And, mechanical took 4 meetings too long, and programming, won't have time. So you got to wire it up in a meeting, when really the wiring should take, 8 hours or more to do and to really do properly. And so we want to make sure that we have that. Sometimes it sounds like this stuff is exactly, what George said is boring, but if you look at every sports team right now, that football team is having 2-a-day practices out in the hot sun. They're going to the weight room, they're practicing these things. So sometimes for us with FRC, it's a sport of the mind, so we have to practice, but we also have to practice the hands-on stuff. Sometimes at a bench. So.
Any questions?
None? Wow. Okay.
Doesn't sound like it. It was a perfect lecture.
Perfect lecture. They all fell asleep. I'm glad we could all read you a nighttime story.
That's right. All right. So we'll see you all on Wednesday. Have a good night, everyone.
Need some time to process.